you for attending the Emerging Trends in Technology Network's virtual education session. This is the 5th installment of the virtual education sessions dedicated to providing more in-depth knowledge for the members, specifically engineers. I've pre-recorded today's session on the basics of diesel engine emissions and aftertreatment systems. And in just a minute, we'll go ahead and start the video for you. But I just want to let you know that I'm going to be online throughout and available to answer questions during the presentation via chat message and then afterward via live Q&A. Here's a brief outline of what I'm going to talk about. I'll give you an introduction to myself, and then we'll talk a little bit about diesel emissions and where they're formed and the health effects of them and how they are regulated. And then I'll give you a little bit of basics on what it means to have something be a catalytic converter, what a catalyst is, what a wash coat is, what a substrate is, and then we'll talk about the specific devices. I threw the gasoline three-way catalyst in there too because I think that's one everyone can relate to. But we'll go through the diesel aftertreatment devices, which are the oxidation catalyst, the particulate filter, selective catalytic reduction, the ammonia slip catalyst, and then I'll talk to you about very briefly, lean NOx trap and passive NOx adsorbers, just to give you an idea of the full range of things that you may see in an aftertreatment system. And then I'll briefly go through some aftertreatment system architectures for some vehicles you may know. So I am Dr. Andrea Strzelec. My PhD is in combustion engineering from the University of Wisconsin-Madison. I am a graduate, proudly, of the Engine Research Center, and I did my PhD work in residence at Oak Ridge National Laboratory. Currently, as I mentioned, I am the program director of the MEAS program at the University of Wisconsin, where I also teach in that program. And before that, I was a professor at Texas A&M and Mississippi State, and I've also worked at 2 U.S. national labs. Additionally, I also literally wrote the book on automotive emissions regulations and exhaust aftertreatment systems. You can see there, pointing to the Strzelec, that's me. So let's start with talking about what diesel engine emissions are and why we regulate them. So the regulated emissions, also called criteria pollutants, are things like particulate matter, also referred to as soot, the nitrogen oxides, NOx, NO, and NO2. One thing to just point out, the oxidation state of a nitrogen atom in an NO is a +2. And in NO2 is a +4, meaning that NO2 is a stronger oxidizing agent. And so when we talk about NO and NO2, NO2 is one we're going to pay specific attention to because it's worse. We also have hydrocarbons. So the hydrocarbons are things like methane, ethane, propane. People think of it as unburnt fuel. That's not really necessarily true. We do a pretty good job of burning the fuel, but it's the partial combustion products that we see in there. And then some of the heavy hydrocarbons, which are derived from like the lube oil base stock. So as you get oil consumption during combustion. And then of course, carbon monoxide. So when you look at a diesel flame, you have direct injection of the diesel fuel into the hot compressed air in the combustion chamber, right? That's how we initiate diesel combustion. So it's very different from gasoline premixed, where you have a homogeneous charge, premixed air and fuel that goes in and gets compressed together. In diesel, right, we only see the air compressed, and then the fuel is introduced through direct injection. And it results in this very unique flame structure. Now, kind of looks like a sideways ice cream cone there, right? 2 of the criteria pollutants that we just defined, soot and NOx, are formed in different regions of the flame, and it really has everything to do with the local temperature and the local fuel-air ratio, right? So you see here we have the soot concentration is high when we have this yellow color here, right? This very hot, very low oxygen region of the fuel plume. So soot is really particularly interesting. Particulate matter, or soot, that gets formed, as I just showed you, in the rich conditions within the flame from each fuel spray jet. So typically you have a 6-hole nozzle, so you have 6 of those plumes identically coming out across the chamber. And the soot is made up of aromatic rings and fragments of partial combustion products, right? So there's a lot of chemistry words in there, but essentially you have these larger carbonaceous molecules that form these aromatic rings coming from some of the naphthas in the fuel that create these physical structures of particulate matter. Particulate is composed of four materials. The black carbon, what we think of as soot, right, which is just elemental carbon. It's essentially coal, right, or like charcoal. An organic fraction, and when we talk about the organic fraction, we tend to use two names, either the volatile organic fraction or the soluble organic fraction, and the difference is how we get it, how we remove it from that black carbon. So it's volatilized off, and that's the lighter fragments, typically from the fuel, and the soluble fraction is typically from the lube oil. We also have ash. Ash comes from the performance-enhancing additives in lube oil, the detergents and the lubricity agents. And it's the stuff that will not burn. And we'll talk about that a little bit more when we talk about particulate filters. And then sulfates. And sulfates were the primary driver for reducing the sulfur content in now what's called ultra-low sulfur diesel, ULSD. 15 parts per million sulfur, and sulfur could have impact on all these different catalytic devices, and so it was really necessary to remove it. The NOx, on the other hand, you know, we think of nitrogen as an inert gas, but at very high temperatures, it becomes reactive with oxygen. And so there's something called the Zeldovich mechanism that I'm showing you there, which occurs again at pretty high temperatures. And so we quickly approach this equilibrium of the NO formation when we're at those high temperatures. And so we can move back and forth between, that's why I have an equal sign, that means a double-ended arrow, the reaction can go both ways. But that process of shifting back towards the nitrogen and oxygen is kinetically limited as the exhaust cools during expansion. So the problem is, you reach these high temperatures, you drive the reaction forward, you get a lot of NO formation, and then as you might be trying to equilibrate and drive some back towards N2, you start the cooling and you drop below the active temperature for this reaction. So that concentration in excess of equilibrium, the so-called super equilibrium concentration, is essentially frozen in by the temperature drop. So also injection timing has strong effect on NOx. So we see that although we know that there are trade-offs between you know, NOx formation and brake-specific fuel consumption, which kind of limits our ability to use injection timing to our strategy. And then the NOx PM trade-off also constrains the calibration of our engine. There are islands that people talk about, you know, that you can chart a path where, you know, in some places more soot gets formed and less NOx gets formed. And then there are places where they're both low, but it's really difficult to operate within that regime. For NOx control, one of the primary ways that we deal with NOx is by avoiding its formation, and that's what exhaust gas recirculation, or EGR, does. We use it to increase the heat capacity by pushing around a lot of gas that's already burnt. So you can think about it as loading more people into an elevator. The elevator is not going to get as high, right, if we've added all this weight into it. So by adding all these things that are not participating in the reaction because it's already spent exhaust products, they can suck up some of the thermal energy of the heat release that happens during combustion, and it'll keep your temperature below that Zeldovich reactivity. Very, very handy for avoiding NOx formation. But again, we're limited on how much EGR we can do to keep combustion efficiencies up. So why do we care about these emission species anyway? Well, remember I mentioned that NO2 in particular is a really strong oxidizing agent, and that means it'll do things like attacking your lung tissue. So, some lean after treatment systems that we're going to see emit NO2, and we're going to talk about that and how we can actually make use of that NO2 in a positive way. But we definitely need to deal with it because, again, it will be really problematic. It's such a strong oxidizing agent. We don't want it out in the atmosphere. And the other problem is with CO. I think we're all familiar with carbon monoxide as a poison. It acts by displacing oxygen from your hemoglobin. So it means that your blood cells can't actually carry oxygen to the tissues that you need it, and you'll cause shortness of breath, and high concentrations, of course, can cause death. The other thing is photochemical smog and ozone. Today, photochemical smog is a more widespread problem than conventional smog. You can see a picture there. And that's because photochemical smog is a complex mixture of pollutants that includes ozone and aerosol particles and that are photoactivated by sunlight. It's predominantly limited to urban areas, mostly in the summer. This is why some of the logic behind the summer and winter fuel blends. And of course in urban cities where you have a lot of pollution. Ozone is another really strong oxidizing agent that has both acute, meaning fast acting, and chronic health consequences. And these have been determined over a number of years through animal exposure studies and epidemiological studies. So ozone at the ground level, very bad, right? We probably all remember as kids hearing about holes in the ozone layer. Ozone up in the stratosphere, very good, helps create a protective layer. Ozone down at ground level, very bad for humans and animals. Okay, let's talk about catalytic converter basics. All of the devices I'm going to talk about today are in fact catalytic converters. Mostly when people talk about catalytic converters colloquially, they mean the automotive three-way cat on gasoline cars, because that was kind of the first one ever. But any device that contains a catalyst and converts species is in fact a catalytic converter. So what do I mean by catalyst? Well, a catalyst is a substance that's both a reactant and product of a reaction. It's not at all consumed or changed by the reaction. So the catalyst is represented by this red part here. And if you notice, here's the catalyst at the beginning of the reaction, the catalyst during the reaction, and the catalyst after the reaction. Not at all changed by the reaction. But what it does do is it increases the rate of reaction. So notice I have two reactants coming in. I have a pink and a gray dot here. They bind into the catalyst surface, which gets them close enough. The catalyst gives them a little boost. It's like a chemical matchmaker. And then notice they become different products in the purple and orange products released here. Typically, a catalyst is one of the platinum group metals. So let me show you what that is. So what makes a good catalyst? These platinum group metals. So here they are on the periodic table. These are the ones in this kind of mint green color. Ruthenium, rhodium, palladium, osmium, iridium, and platinum. I like to talk about a chocolate chip cookie analogy for catalyst. So these platinum group metals would be the chocolate chips in my cookie here. These things are really expensive, and I'll show you that in just a minute. SCR catalysts use transition metals instead, copper, iron, or vanadium. And so here's copper. You can see that in that other noble metals. Iron's right here above ruthenium, and vanadium. We'll talk about those. Those are transition metals. So those have the multiple oxidation states. So just like what I showed you before with the NO and NO2 having different oxidation states, things like copper, iron, vanadium, which I'm sorry, I meant to point that out right there, have multiple, they're in that transition metal part of the periodic table, and they can have multiple oxidation states, which makes them very, very handy. Now, the catalyst, we don't just dump like little particles of metal into the devices. The catalyst is held in place by a high surface area support material that's called the wash coat. And it would be this cookie material, right? So in order to put the catalyst into the substrate, which I'll show you in a second, we need something to hold it there and hold it in place. And that's the role of this cookie material. That's the wash coat. So remember, the chocolate chips are the platinum group metals, and the cookie material is the wash coat. These PGM catalysts, we talk about how much of them are on the catalyst by talking about the loading. The loading is given in grams per liter, and it depends where the liter is the volume of the full catalytic converter device. And how much you need depends on a number of things. It depends on emission standards, it depends on what your engine is putting out, and it depends on how much you can afford, sort of, because they're really, really expensive. So it's important to minimize their use. 1 troy ounce is about 31.1 grams. And you can see the prices here. Platinum is about $1,000 a troy ounce. Palladium is about $2,000 a troy ounce. And rhodium is about $15,000 a troy ounce. These are prices from the 20th of May. These prices are extremely volatile. I plotted some historic rhodium prices here, and you can see rhodium was somewhere around $2,500 throughout 2018 and even into 2019. And then right around here, as the pandemic was hitting, you saw rhodium prices spike to about 15,000, and then they just continued to grow up. These platinum group metals are extremely expensive. They're rare. They have to be mined, and you know, these prices are very, very volatile. You can go to this Umicore site. Umicore is one of the automotive catalyst suppliers, and you can, you know, take a look at what prices change twice daily, and you can see these kinds of historic plots of these things, and it's really amazing how these things change. If you're interested, vehicles that have like a PZEV designation, those typically have the highest catalyst loadings on them, so those will tend to be very expensive, and that's why you see catalytic converter thefts on cars like Priuses, because they have so much catalytic loading. It's worth a lot of money. So the problem with catalysts is they don't change as a course of the reaction, but they can lose functionality by inhibition. Inhibition can be reversible, or you can poison the catalyst, and that can be irreversible. Things like phosphorus from the lube oil or sulfur from the fuel. So again, this is one of the reasons why we had to get the sulfur out of fuel, can have a big impact. The other way catalysts can lose activity is by reduction in surface area. So the platinum group metals and support materials at high temperatures can migrate and sinter, right? So you've seen that coalescence of like raindrops on your windshield, same kind of thing, right? The surface tension forces pull them together. So you have all these little mini chips, and then due to temperature, they all get glommed together and make this one big chip. And so the problem is, for the same amount of mass, you have less surface area in one big particle than you do in all these little particles. So for the best activity, we want mini chips in our cookie, not one big chunk, right? The wash coat, that cookie part that I talked about before, serves as a carrier and for the PGM particles, and it binds them to the support. So we want it to have a high specific surface area and good thermal stability, right? We want it to help hang on to those chips and keep them from migrating. The most common support material is an alumina, which is Al2O3, and then you can have other various things on there, including some like cerium and zirconium oxides, which are useful for oxygen storage in three-way catalysts and lean NOx traps, and we'll talk about that a little bit more. The catalyst substrate is the actual physical brick that we put the catalyst and wash coat onto. It's there to provide the surface area for the reaction between the exhaust gas and the catalyst species. When you design one of these substrates, you need it to have high geometric surface area, low heat capacity, right? You don't want it swelling outside of the can material. It has to be able to withstand high temperatures for exhaust. You need it to be oxidation resistant so you don't burn it up as it's in the exhaust. It needs to be strong. You need to be able to paint the wash coat onto it or slurry the wash coat onto it. So those are all things that we have to take into account when we're planning a substrate. Once you have the catalyst containing wash coat coated onto the substrate, the next step is to do what's called canning, and that's when the whole device becomes a converter. So the wash coated substrate is packed into stainless steel housing, and that's what allows you to connect it to the vehicle. At that point, it's referred to as a converter. So what we care about at the can is good flow distribution. So remember, you have about a 3-inch exhaust pipe here, and this is about a 6-inch substrate brick. So you're going to have a diverging nozzle, right, that you, or diffuser on the front end of the can to take that flow and spread it out to hit the whole front face and flow through the whole catalyst. That ceramic catalyst is wrapped in a fiber mat. That mat does a couple different things. It helps immobilize, right? It creates a compression fit within the can so that the ceramic doesn't get shaken around and turn to powder. It also does help with some thermal stability issues in there. So now let's talk about, now that you have some basis for it, let's talk about the exhaust after treatment devices, the so-called catalytic converters that we see in the exhaust. So I want to start with the gasoline 3-way catalyst. For gasoline, the priority pollutants that we care about are hydrocarbons, CO, and NOx. And gasoline is a really special case because due to the nearly stoichiometric air-fuel ratio in gasoline, we can get away with just using one catalyst, and it's called a redox catalyst because it simultaneously reduces NOx and oxidizes the hydrocarbons in CO. So they take place in such a beautiful paired harmony. It's really awesome. So the chemical reactions we have is CO and hydrogen oxidation and NOx reduction, and you see that the reducing agent here, so the CO and hydrogen would be the reducing agents, are going to steal the oxygen off the NOx and become oxidized. And the oxidizing agent is going to donate its oxygen and therefore be reduced. So that's why it's a redox catalyst, an oxidation reduction catalyst. This is the one that most people mean when they colloquially say catalytic converters, but again, all of these devices are in fact catalytic converters. The 3-way catalyst, the platinum group metals on there is typically platinum, palladium, and rhodium. The platinum and palladium are the meeting place for the oxidation reactants, and the rhodium is the meeting place for the reduction reactants. The chemical reactions going on here, here's the CO goes to CO2. The hydrocarbons, and I just have a model molecule there, becomes CO2 and water, so completes that combustion. And then the NO gets reduced to nitrogen, and with the aid of a CO, which gets oxidized to CO2. There's a really nice video from BASF. It's about 2 minutes, and a woman with a lovely British accent will talk to you about a little bit more specifics about the flow through these. But here's the main event. What we're here to talk about today is diesel aftertreatment systems. So unfortunately, while gasoline can get away with just one catalyst, due to the lean operation of a diesel engine, there's still a lot of oxygen around in the exhaust. So a redox catalyst would only be able to oxidize. Therefore, we need to split that redox functionality up into multiple devices. And so we have the Diesel Oxidation Catalyst, the DOC, which takes the oxidation portion, and the Selective Catalytic Reduction Catalyst that takes the reducing portion of that. And in diesel systems, we also now have another criteria pollutant that we care about, which is particulate matter. So we have to add in yet another device, the DPF, a diesel particulate filter, to remove the particulate from the exhaust. So what was one device now becomes the DOC, the DPF, and the SCR. And for a couple reasons, sometimes there's yet another catalyst after the SCR, the ammonia slip catalyst, that has to clean up some of the stuff from the SCR. And sometimes up front, there's yet another device called like a passive adsorber that we have to use until the exhaust is hot enough. So the diesel system is significantly more complicated than gasoline. Okay, so let's start with the diesel oxidation catalyst. Its function is oxidizing hydrocarbons, CO and NO. And if you're like, wait a minute, I thought NO2 is worse. Well, it is, but there are some benefits to having NO2 around for the later catalytic devices. So there will be, spoiler alert, some benefits to having NO2 around in both the DPF and the SCR, and we'll see that. So that's why it's handy that the DOC makes some NO2. The light-off temperature for the DOC is around 200 to 250 C, so it's something that can get heated up pretty quickly. Light-off is specifically where 50% conversion of the emission species is achieved. So where we're at least converting 50% of the incoming CO and NO and hydrocarbons. The DOC is best if it's close coupled to the engine, so it gets hot really quickly. And the first 20 seconds of diesel operation tends to have to be a little bit fuel rich in order to get the DOC hot quickly. And the time before the DOC is hot is when tailpipe emissions are the highest, and that's why we tend to focus on cold start testing for emissions reasons, like for EPA compliance. Once it is at its normal operating temperatures, we see very high conversions, better than 98%. So again, it oxidizes the partially combusted hydrocarbons from the fuel or any of the VOF off the particulate matter. It oxidizes the CO to CO2, and it oxidizes the NO to NO2, which will be useful to the DPF and SCR. For the substrate, the DOC is what's called a flow-through monolith, meaning there are no plugs. So see this, all of these channels, the gas is just going to flow through. So it can be made out of ceramic or corrugated metal. And the cell density, the number of channels you can have here, is limited by the possibility of plugging the face of it with particulate. So theoretically, you want to make sure that the gas is going to be in contact with the catalyst. So theoretically, you want as many channels, as many tiny channels as possible, right? So that you don't have a diffusion resistance to getting that gas in contact with the catalyst. The most common DOC platinum group metal catalyst is platinum palladium, a mix of the two. Some are platinum only. The reason is NO2 formation occurs on platinum sites, but the platinum palladium alloy has better resistance to sintering, like I showed you before, right? That's where all the little chips become one big chip. For the wash coat, we want something that's high surface area, so we use like mesoporous aluminum, and it may include some zeolite materials for hydrocarbon storage before light off. So that's what we call a passive adsorber. So if it's not hot enough, a zeolite is a molecular sieve, and it can hang on to the hydrocarbons until we get hot enough so that we can start, then the zeolite material can release them and they can be chewed up by the DOC. This is a requirement in the passenger car side of life. It's not a requirement in the heavy duty trucks. And the size of the DOC is based on the maximum space velocity it's going to see, right? So that's the engine displacement, right? What we look at for space velocity is we take the engine displacement, right, which is going to be in liters per minute or liters per second, and we're going to divide it by the volume of the catalyst, and we're going to get a time in inverse hours, and that's how many changeovers the DOC is having during that time. The higher that number, the faster the gas is flowing through there, and the harder it's going to be to achieve the conversions of the gas, because these reactions take time, right? Briefly taking a look at DOC performance, the DOC light-off temperature, like I said, is 50% conversion, so I have this dashed red line at 50%. The light-off temperature is a function of a couple things. It's the platinum to palladium ratio. So you can see all of these legends correspond to the ratio of platinum to palladium. So this first one is all palladium and this last one is all platinum. It's also a function of temperature. Notice how all of these plots change as a function of temperature on the x-axis here. And it's a function of species. So notice here this is methane and this is decane. And what you see is all palladium is best for methane, but worst for decane. So it's really, really interesting the number of variables these things depend on. This all has to be measured via bench testing with compressed gas cylinders and some really high quality equipment. Over here, this is NOx, and whereas before what you saw is universally for the hydrocarbons, the higher the temperature, sort of the better the situation, regardless of platinum-palladium ratio and species. For NOx oxidation, what you see is that higher temperature is not always better. And so what we see here is some differences in the mass transfer versus kinetic control. So whether it's a matter of getting the species from the gas to the catalyst surface, or the actual rate of reaction is what changes the shape of these plots. For the next device is the diesel particulate filter. So particulate filters are really necessary for controlling soot emissions from diesel engines, and they are quite honestly necessary for GDI as well. So you're seeing them come on the market as GPFs for gasoline particle filters. What happens is we have particulate removed by filtration. So now what you'll see is alternate channels in that monolith are now plugged. So gas and particles go in through one channel and then the gas will exit through the neighboring channel. So these are what's called wall flow because the flow goes through the wall. So it's really just mechanical filtration, and then periodically we have to get rid of the stored particulate. So we do an oxidation process called regeneration. The two functions of a diesel particulate filter are the filtration and regeneration. So first up, filtration. The filter mechanically filters the solid particles from the exhaust. Again, the gas has to go through the wall. So the gas can go through the wall, but the particles get trapped in and on the wall. And so there's a variety of different filtration mechanisms that happen there. But what really matters most is a brand new clean DPF may start as low as 65% filtration efficiency captured by the wall, but it very, very rapidly increases to better than 95% as a soot cake forms on top of the wall. So you can see here these green dots represent my porous wall, but you can see that so much soot has come in so quickly that they have done what's called pore bridging and created a layer on top of here. And so as these particles pack in, you see that the interstitial spacing between them is actually smaller than the spacing of the wall pores. And then the cake itself becomes the major filtration mechanism. So when we talk about filtration efficiency, it's the relative percentage of particles that are trapped by the filter. We can either calculate it on a mass or number basis, and which one you do depends if you're in the US where we like mass or in Europe where they like number. Again, filtration efficiency starts out pretty low, relatively 65-75%, but it quickly reaches better than 95% as you have this soot cake that develops on the wall of the filter. So what happens is the pressure drop across the device grows really quickly until the cake has formed, and then once the cake exists, the growth becomes slower as the cake takes over the dominant filtration work. The second function of a DPF is regeneration, and that's as you collect all this, coal dust essentially in there, after a while, right, you end up with this high back pressure on the engine, and engines, like people, need to breathe. So if they can't breathe out, they can't breathe in, you'll start to retard your combustion process. So periodically, it's best if we clean out the stored carbon in the filter. And so what we can do is we can do that either continuously through passive processes, or sometimes you just create a burn event and burn things out. So if you create that event, it's what we call active, right? You actively did something. Or thermal regeneration, which is an intentional process that occurs periodically. Often pressure drop is used as the indication that it's needed. And the reaction becomes carbon solid plus oxygen forms CO2. It requires temperatures of at least 550 C. So that's why it's an active event. We have to do something to get there. We can heat the exhaust in a number of ways. We can use the DOC, so you can use a late fuel pulse in cylinder while the expansion work is already coming. So very little of that fuel burns or that heat release happens because you're already cooling down as you're doing that expansion work. And instead, that fuel burns over the diesel oxidation catalyst, doing the heat release there and raising the temperature of the exhaust enough to light off the DPF. Now, if you do this too often or you don't do a good job of this, it results in significant fuel penalties and you can potentially damage the particulate filter. So control of these guys is really, really important. The other way to do regeneration is what's called passive regeneration. And if it happens, it's going to happen continuously, but it only happens under specific operating conditions. For passive regeneration, the oxidizing agent is actually NO2. So this is where it's handy that we form some NO2 in the DOC, because NO2, when it's around and when the exhaust temperatures are like 275 to 400 C, does a really great job of oxidizing stored soot. And that's very, very helpful for us, right? So it keeps us, it reduces the time between when we need to do active regenerations. Ash accumulation in the filter impacts the service life. So ash, I mentioned before, it's the non-combustible material that's left behind after a regeneration, or the non-combustible material that comes in from the combustion chamber. It's things like lube additives like zinc, calcium, magnesium, phosphorus, sulfur. So it can come from like detergents like ZDDP that puts a lot of phosphorus into the system and can create a lot of ash. Calcium, zinc, those are all things that appear in the lube oil. It can also be like engine wear and corrosion products, so metals, or trace inorganic elements in the fuel. And you see these like ash particles over here. I know it looks like some sort of weird space age thing, but these are ash particles that have accumulated in a DPF. The problem with ash is it occupies filtration volume. So here is an amount of soot in a filter that has no ash. And you see this amount of soot makes these little thin coatings, and this is what the channel looks like. It's coated with soot in the corners and all that, but there's still a flow path. If you have ash in the filter that's already taking up the filtration volume, that same amount of soot creates a much thicker layer on the wall, and it leaves a lot tinier flow path in there. So the ash affects the flow through the DPF and of course the pressure drop performance. So it accelerates the formation of a soot cake, which is pretty good for increasing filtration efficiency, but it reduces the available flow volume down the channel and creates some back pressure effects on the engine. So realistically, it also means that you have to do your active regenerations more often. Next up is the Selective Catalytic Reduction Catalyst. So this one reduces the NOx from the exhaust with the use of an additional reductant, which is a urea water solution. Urea is a salt, and we mix it in with water to create the urea water solution. Or the EPA were a little bit hesitant about what kind of connotations people might think about when they heard urea, so they gave it the name diesel exhaust fluid, DEF. Or there are brand names for the urea water solution. For example, AdBlue is a trade name of a urea water solution from a specific manufacturer. How selective catalytic reduction works is you inject the urea water spray into the exhaust. So you have your oxidation catalyst here and then the DPF usually after it. Then you have an injector, so just like a fuel injector, that doses the urea water solution in here and sprays it before we have the urea SCR catalyst. So the urea water spray gets injected, the spray evaporates, and the urea thermally decomposes into ammonia, and ammonia is the actual active reagent that enters the SCR and reduces the NOx. There are 3 chemical reactions associated with selective catalytic reaction. I'm going to talk about these again in a minute, but there's the fast, slow, and standard reactions, or fast, standard, and slow. But what you see is sometimes there's the reaction is happening with just NO2, sometimes it's happening with NO and NO2, sometimes just NO, and these are the 3 SCR reactions. Now, the one thing I want to point out here, though, is there's all this ammonia that we need, and we're going to talk about in a second that it's really important to have enough ammonia to get these reactions going, so that might mean you dose with a little bit extra, but ammonia is a regulated emission, and so that is why sometimes there is an ammonia slip catalyst, an ASC, after the SCR that is there to oxidize any ammonia in excess in the SCR. The problem is when you oxidize this ammonia, you're going to form NO and NO2, so you're sort of undoing the good you did. So you have to be a little bit careful about that. You don't want to oxidize it. You don't want to overdose because you don't want to create the same problem that you just cleaned up. Looking at the ammonia introduction system, first we looked at what if we just put ammonia as a gas on board the vehicle. So we could do this process a little bit easier, but I don't know if you know, but ammonia can be explosive, and stored as a gas under pressure was considered pretty unsafe for mobile applications. So although it's kind of annoying to do this whole urea water spray thing, it's really difficult to displace because, it's pretty safe. Significant capital has been invested in its infrastructure, and we know how to do that now. So again, DEF stands for diesel exhaust fluid, and it's what you'll often see the urea water solution sold under. The urea introduction system is a tank, so you have to have a DEF tank. You have to have some sort of level sensor to know how much is in there. You have to have some sort of heater in case it gets cold and you have to thaw it. You need a pump that takes it to the injector system. You need that nozzle so you get to spray it into the exhaust. So it does represent significant cost, but unfortunately it's the safest way we have to introduce the ammonia into the system. Okay, here are the 3 mechanisms I mentioned before. So the standard SCR reaction is the NO only. It was my middle equation on the last slide. It has a 1-to-1 stoichiometry with ammonia. So you see there's 4 ammonias to 4 NOs. There is the fast SCR reaction, which requires NO and NO2. So again, this is the benefit of having that DOC promote the nitrogen oxide to NO2. And together they have a 1-to-1 stoichiometry with ammonia. So 2 ammonias, 1 NO, 1 NO2, boom, fast SCR. And then there's the slow SCR reaction, which is with NO2 only, and it requires a much higher ratio of ammonia per NOx. It's a 4-to-3 here, 8 ammonias to 6 NO2s. And so this one is so slow that most of the NO2 gets used up in this fast NOx reaction. The problem with SCR, though, is that you can have byproducts, right? We talked about the ammonia slip, which may require an additional catalyst, so yay, more things on the vehicle. We then, in that ammonia slip catalyst, might create more NO or NO2 from going backwards from ammonia, the wrong way. And when we're oxidizing that NO and NO2, we may also form N2O as a byproduct. And, If you think CO2 is bad, N2O is way worse. It is a regulated greenhouse gas pollutant with 300 times the global warming potential of CO2. And we deal with trying not to make it by counting against CO2 emissions for on-road vehicles. So that means you can handle very, very small, single-digit part per million amounts of N2O formed. And then the other thing that we sometimes worry about is ammonium nitrate formed as a byproduct, which can form at low temperatures, and then we can crystallize that and be in the exhaust. So these are things that could happen if we don't control our SCR process well. So looking at the SCR performance, it depends on a couple things. It depends on how much ammonia storage capacity we have. The copper version of the zeolite has, I mentioned 3 kinds before, right? Copper, iron, and vanadium. The copper has the highest capacity and the vanadium, titanium the lowest. It depends on temperature. So you see NOx conversion increases from 150 to 250. So that's the light-off behavior we were looking at before. And then stays pretty stable until some of these higher temperatures we start to see the drop off. For the vanadium and copper, we do see some parasitic ammonia oxidation causes the NOx conversion efficiencies to decrease, and that's because we're forming NO and NO2 by oxidizing the ammonia. Again, the effective space velocity is important. So as you have higher space velocities or push the gas through the device faster, there's less time for the reactions to take place because there's not as much time for the gas to diffuse to the surface where the catalyst is. So that's what's called mass transfer control. Again, you can see that the effect of the NO2 being present on SCR performance varies with the type of catalyst it is. So if you look at these various species, you can see that this is vanadium, this is an iron catalyst, this is a copper catalyst. You can see that having different amounts of like just engine out NO2 or moderate NO2, meaning we've added some in, or high levels of NO2 change the conversion efficiency, and the order of the lines changes for each of these materials. Okay, so I've previewed it several times, the ammonia slip catalyst. Again, its motivation is because ammonia is a regulated emission, and we can have significant amount of ammonia leaving the SCR if we overdose with a high ammonia to NOx ratio. Again, just straight up oxidizing the ammonia would lead to NO and NO2, which would undo the NOx conversion. So what we do is we make a dual layer ammonia slip catalyst behind the SCR, which performs some bonus NO conversion. So you see here we have a dual layer catalyst. The blue layer is the SCR component, the gray layer is the ammonia oxidation component, and the green layer is representing that substrate. So what happens is the gas diffuses in, and on the gray layer, the ammonia oxidizes to NO or NO2. And then as it's diffusing back out and through the blue layer, the SCR reaction takes place, and we create nitrogen, right, and get rid of the NO, NO2 that we used. So the ammonia slip catalyst is brilliant because it oxidizes over a broad range of conditions. The ammonia that gets partially oxidized to NO, the NO and any unreacted ammonia react by the standard SCR reaction in the blue layer, and we have bonus NOx conversion in the ammonia slip catalyst. So this dual layer situation is attractive for both getting rid of the ammonia and again doing some bonus NOx conversion. There's another device you should be aware of called the lean NOx trap. The lean NOx trap was at one time a competitor for the NOx cleanup, the SCR one, but there's a few opportunities where lean NOx traps are used, so I want to at least let you be aware of them. The lean NOx trap stores NOx under lean conditions, so that's the trapping part, and then it reduces it during stoichiometric excursions. those excursions are referred to as regeneration, or the denox portion. So you suck it up like a sponge under lean conditions, and then you do a periodic rich condition, and you do your denox. Same kind of regeneration that we saw in the three-way catalyst. In fact, the lean NOx trap is very, very closely related to the automotive three-way. The LNT converts both the hydrocarbons and CO under both lean and stoichiometric conditions. So you can see that very, very similar to the three-way catalyst we talked about before, because it only reduces NOx under the rich conditions, and sometimes the LNT may be substituted for the DOC. Not very common, but there's a few out there, so good to be aware of. And then the final device I want to talk about is the passive NOx adsorber. A passive adsorber absorbs NO at low temperatures and releases it at higher temperatures. So again, same idea. Sponge sucking it up at low temperatures before conversion can occur, and then lets it out at higher temperatures. And we use it to align the NO release when the SCR is hot enough. So they're not always used, but they really do a good job of taking care of the cold start NOx emissions, because they just hang on to them until it's warm enough. What drives after treatment systems? Well, the whole reason we have to have them is because of global emissions regulations, which are not all the same. Fuel prices drive after treatment system design. The application requirements, whether we care most about performance or packaging or reliability, and then costs, right? Current cost reduction efforts of what's called thrifting of those platinum group metals is another thing that we work on. And the cost of an after treatment system can be significant. This is from an ICCT publication, and you can see that over the years for a diesel after treatment system in 1998 versus 2004 all the way up to 2010, so it's even more now, has gone from about $50 to about $7,000 for the various components there. So you can see the cost there, and if you click on this link, you can look at ICCT comparing it over a wide range. I know I'm running a little short on time, but I wanted to at least connect this to some systems you were probably familiar with. So light and medium duty trucks. So Ford, GM, and Cummins produce engines in the 6 to 7 liter range that we see in light duty and medium duty applications. Light duty applications would be pickup trucks below a certain curb weight, and those fall under the EPA LEV 3 Tier 3 requirements, which means the same for passenger cars. And those have more challenging cold start than, say, medium or heavy duty standards. It would be really nice, though, to have a single after treatment system that meets performance requirements for both sets of regulations. And so in some of these 6 to 7 liter range engines, they may be applied in either a light duty pickup truck, or they may be in a medium duty application. So maybe something like a class 3 vehicle. And so ideally we want to create just one after treatment system to be used in all of them. So some examples, here's the 2007 Dodge Ram. Cummins uses an LNT enabled system in this, and so even in 2007 they met the 2010 standard, which enabled them to accumulate a whole bunch of credits for later use. This is the example of the largest displacement engine where a lean NOx trap has been applied. It's no longer in production, and the durability requirement was achieved through very, very careful design of the desulfation characteristics. The 2010 Ford F-250, so this is often lovingly referred to as the torpedo. My friend Dr. Christine Lambert at Ford won several awards for this design. This is a single tube design with SCR upstream of the DPF, so that was really interesting. It means that we completely lose any ability to do passive regeneration in the DPF, but they used a substrate that enabled a high temperature substrate that enabled higher soot loadings and longer regen intervals, so they didn't rely on the passive regeneration as much. Here's a 2010 GM pickup. Once again, we have the SCR upstream of the DPF, and you see the DEF tank is located on the side of the engine compartment. Here's that urea tank right here, kind of an unusual location for it. In 2017, one modification is a second DOC was added between the SCR and DPF, and that's to enable, again, some of the passive regen, and also to get the exhaust hot again to allow the DPF regen. And in 2013, Cummins switched to a DOC DPF SCR system in the Dodge pickup. So this is what we think of as kind of the typical arrangement: DOC, then DPF, then SCR. That's why I sort of showed them to you in that order. And looking at on-highway trucks, so Class 8 trucks have a very well-defined duty cycle, but medium-duty trucks, you know, your Class 3 through 5, can be very variable in their application and operation, right? These are things like your UPS trucks, or, you know, small box vans. And completely different technology pathways were chosen if you are in Europe or North America initially. Let me show you some examples. So here are some really interesting variants, right? You see this Cummins single module, you see this Daimler box design, and you see Volvo Max setup here. Very, very interesting different designs on the heavy duty. And if you want to learn more about that, you can look at this QR code that'll take you to the engine courses that we offer at UW, and there's a whole 2-day course on nothing but emissions control systems, and we get into the nitty-gritty of all these systems. So looking at future system architectures, the low NOx standard for heavy-duty trucks are kind of finalized now in North America and Europe. The SCR system, which is highly efficient at higher temperatures, but it's a little bit more challenging during cold start and under sustained, like, low load operations. So trucks, you know, driving at low speeds, maybe through town delivering vehicles. And the new regulations put a lot more emphasis on both of these aspects, because these are times when a lot of emissions are coming through. So there's a lot of interest in technology packages that we're looking at now to do higher NOx conversion. And actually last year I won a big grant from DOE to work on just that. And, you know, the OEM technology packages might also include components focused on improving fuel efficiency associated with these devices, especially now that diesel is ranging up somewhere around $6 a gallon. So very, very tough times. With that, I just really want to thank you so much for the opportunity to present to you. I'm very happy to take questions live and in person now. And you can also feel free to email me if you have questions, or connect on LinkedIn. And again, this QR code will take you to our engine course page, whether for the master's degree program that I run, or a couple capstone classes, or if you just want a couple days seminar on a particular topic related to engines, you can find it right there. Thank you very, very much. Okay, so thank you everyone for watching that video, and thanks for the great questions in the chat throughout. It's been really interesting to see what kinds of things folks are focused on. I see a question Jeff Harris is asking, is there a PDF of this presentation available? Unfortunately, no. Through University of Wisconsin, we have a version of the class that people can take, and so I couldn't make this presentation available. The video will be available, and so there were some really great questions. There was a great question that I wanted to address too, back up here a little bit, which was about if the EPA and CARB specifically require these specific devices, and the answer is no. And that's really how the difference came up between, like, the LNT and the SCR. The LNT is really a very close cousin to the three-way catalyst, And so initially, as you know, NOx became a bigger problem for diesels, people thought, well, we've got this lean NOx catalyst. It really works great under a lot of these conditions. Is there a way we can just modify it, to deal with the NOx situation in diesels? And so that was one school of thought. And then other folks said, no, this is never going to work. We're never going to be able to make the LNT work. We got to come up with some sort of different device. And they came up with the SCR. And for a long time, it was sort of neck and neck over which technology was going to win. And and then there was Navistar, who said, forget it, we don't need to add any additional technologies. We're just going to handle the NOx through EGR alone. And that's the bet that they made, which turned out to be a bad bet. And then they ended up having to buy Aftertreatment from Cummins. So no, specific devices are never required, although folks in the aftertreatment field will sometimes jokingly refer to the EPA as the Employment Protection Agency. They don't require our specific catalytic devices. On the other hand, they do sometimes require that you do your emissions testing with specific devices. And often those were, in fact, developed at EPA or CARB. I think I'm caught up in that case on questions in the chat. If there are others, I'm happy to address them. Or I think we may have hit the end of our window.
I don't think there's any more coming in, so I think you're good.
Okay, in that case, I just wanted to thank everyone again for joining us today, and you'll be able to view the video of this session within the next day or so at SEMA.org/education. You'll receive an email notification when the video is available. And if you have any questions about today's presentation, you can email me at strzelec@wisc.edu. My email was on that last slide. I'll toss it into the chat as well, just to make it easy. I know my last name can be a little bit tricky to spell. Or you can ask questions on the discussion tab in the video. And if you have any questions or comments regarding SEMA's virtual education program, please email Gary V at SEMA.org.
Thank you so much, Andrea. We really appreciate you doing this today. It was a great session, and we appreciate all the chatter in the chat box. It was great to see all those questions come through. Awesome.
My pleasure. Thanks for having me.
Thank you.